Have you ever used Google Maps to navigate your ships through the Arctic? Maybe you haven't found the container shipping symbol on Google Maps, or you didn't trust the delay it calculated due to ice conditions. My name is Lasse Rabenstein. I'm co-founder of Drift and Noise Polar Services. And of course, nobody uses Google Maps to navigate through the Arctic. But today I would like to present you a strategy that how this can become reality, not in Google Maps, but in general, how we can calculate automatic routes and optimized routes in the Arctic. To answer that question, we gathered with two partners in the city of Bremen in northern Germany. And we started a 2-year research project called MAP-BORealis, which is funded by the German Ministry of Economics and Energy. We defined a lot of competences we need to have to solve that complex problem. For example, we need competences in supercomputing and artificial intelligence. For this, we have our partner, the University of Bremen, more specifically the Industrial Mathematics department there. We also need expertise in remote sensing and image analysis to automatically detect features of ice on satellite images, for example. For this, we partnered up with the German Aerospace Lab. The office in Bremen is focused on maritime research. And last but not least, our company, Drift and Noise Polar Services, contribute with Arctic field experience, with sea ice physics knowledge, and with software engineering. We have a software as a service business model, so we know how to provide such developments in the end as a digital service to you. When we started the MAP-BORealis project, I was afraid that there is quite some skepticism about automatic route suggestions because it might replace jobs in the industry, as you have heard in other sectors as well. So I started a survey, and the survey is actually still ongoing. And if you haven't filled that survey so far, please go to icesurvey.org and do it. We still need more opinions. Presently, it's probably not statistically relevant at the moment. But we gathered first answers, and so far, no one said I would not use route suggestions as an additional information on my voyage. So far, everybody is open to that technology. But they said as an additional knowledge. So we see that this is not replacing jobs of ice navigators, but it is an additional tool to make their work life easier and to make this shipping business more economical and more ecological. Why do they say so? Because, it's another question, we asked ice pilots and master mariners how often they are in a situation in an ice-related voyage. Well, it was not sure what was the most effective and best route to take because the situation was too complex and the amount of information too big to digestion in a short time on board. So we're dealing with a big data problem. So ice routing is a good example where digitization and supercomputing works hand in hand with the human factor and the human expert on board. A good example is the cruise of Kapitan Donitzin to Polarstern this February. Polarstern drifted as part of the Mosaic experiment as a laboratory 1 year into transpolar drift and needed resupplies and crew exchange every 3 months. And the most challenging cruise was the one of Kapitan Donitzin in February, so under winter conditions into the Central Arctic. And this is a voyage which gives us, or which taught us a lot of parameters we need to consider to optimize the route even of an icebreaker who do not want to avoid ice, but who really wants to have the best route through the ice. A very complicated task. So the ship started on February 3 and marched straight to the Franz Josef Land waters. Why did they do so? Because they knew around this region we had first-year ice from this winter and not the heavy multi-year ice and older ice. So we can say that ice type, so the things which are provided by ice charts, for example, ice types is an important factor and our computer needs to know that to calculate the best route. From this moment on, the most difficult part of the Donitzin cruise started into the heavy ice in the Central Arctic, into the multi-year ice. And you see that the daily progress became really, really small. On February 11, this photo was taken. It was dark outside, so there is no routing, no scouting ahead with drones or helicopters. It is really a complicated environment. Unfortunately, they had these Sentinel-1 radar images on board, which are independent of daylight. This is probably one of the most important tools nowadays for ice navigators and ice analysts. On these images, you can identify first-year ice here in darker or multi-year ice here in brighter. You can identify open cracks or ice-rich systems. You can even see the track of the Dranitsin and the Dranitsin itself here in the upper right corner. Such an image was available every 24 hours, more or less. Here's a subsequent image. You still can see how the Dranitsin cruise progressed into the ice, the Dranitsin cruise track. And we note for our computer algorithm, we need high resolution information for this task. For icebreaker assistance, high resolution like this image is needed. An ice chart, for example, is not enough, which always shows a big red blob in the central Arctic. So Dranitsin progressed. At some point, they even went out of Sentinel-1 satellite coverage. That makes it even more complicated. And you see that the progress was really slow. And it was by far not clear that they made it to Polarstern on time, and they had enough fuel on board. You see that the drift of Polarstern was almost the same distance the Dranitsin traveled every day. So they did not really came closer at some point. But the situation changed on February 22. Suddenly they made better progress. What happened? They were still in the same ice, but the ice dynamics changed. Maybe the wind system changed. So the drift of Polarstern slowed down, and maybe cracks and leads opened up in front of the Dranitsin, and they could make better progress through the heavy ice. And finally, on February 28th, they made it. They could exchange crew, supply foods and fuel. And as a last point, I have to add here, for our algorithm, we need the ship characteristics. So Kapitan Dranitsin has different ship characteristics than a nuclear icebreaker, for example. This has to be taken into account as well. Just as an add-on, on the way back, Dranitsin had to be refueled by another icebreaker, so the entire situation was really close. It was by far not certain that this will be a success. And we hope that in the future, with this big data analysis, we can make even such a challenging project more calculatable. Okay, now I will present you the strategy we developed within the MAP-BORealis research project. From the user input, so 2 coordinates, A to B, from where you want to travel, to the output, so a suggested route trajectory. And of course, time is an issue. In Google Maps, people are used to wait 2 seconds or so. So maybe later in the question and answer session, you can tell me how long you would wait, because we don't know, like how long would an ice navigator wait for a route suggestion? 2 seconds, 10 seconds, 1 hour, 1 day. 1 day is probably too long. But we need to have a goal which we need to achieve in terms of calculation time. So the computer gets A to B coordinates, and the computer scales the problem down to the relevant geographical region, so we don't have to calculate the entire Arctic every time. Then in the region, the computer algorithm needs to fetch classified ice information. Where do they get that from? Sentinel-1 imagery is one example. The computer program doesn't want to have radar images, they want to have ice classes on an image. So here's our partner, the DLR, comes into play. They have quite some experience in classify these images automatically into, for example, classes of open water, first-year ice, multi-year ice, etc. This is understandable by a computer. The next step, we need to progress this in time, because the satellite image is static, but when the ship goes along the ice changes. The ice dynamics, you remember from the cruise of Dranitsin. So we need to connect an ice model to it. We use a method we developed at Drift and Noise Porter Services. It's called PRIMA, Predictive Ice Images. So we can animate the satellite image into the future. By this, we create a series of simulated Sentinel-1 recordings. In the end, we have a 4D data space in space and time on which we can optimize the problem. The next step is we need to transform ice classes, which we classified, into an optimizable parameter like velocity of the ship or fuel consumption or risk. We can follow different strategies here, and take a previous project that was also tried to really calculate physically how fast certain ships are in certain ice types. The problem is that even if you can calculate that, you don't have the exact information on the ice. How much snow is on top, how many ridges are there. This is information which is really hard to get, and it's also not resolved on the Sentinel-1 images. So I have another approach here. We do it similar to Google Maps. Google Maps just analyzing your driving behavior continuously. They don't know all about the details, why you stopped here, why you stopped there, why you were slowed down then. But they just collect so many data that in the end, their statistics is quite correct for your case. And we want to do the same. So on these satellite images, we can identify the cruise tracks, and we can analyze the velocity and the speed of the ship and assign this to ice classes. If you do this with hundreds and thousands of images, in the end, we might have a statistically relevant characteristical curve for this particular ship. Next step, we apply a so-called A-star algorithm on this 4D data space, where we have like not only ice classes now, but velocities, for example, to find the best route in terms of velocity, so the fastest route. And finally, we output the entire thing to the trajectory to the user. And within MAP-BORealis, we always want to keep in mind the big picture, the entire end-to-end value chain. We don't want to stop with one problem and just solve that problem first before we go on. But with all three partners together, we want to test a new development immediately in the end-to-end value chain. Give it to the user, get feedback from the user if they like it or not. So here you see a visualization of what's happening in the background of the route optimization. So you have a classified ice field. This could also be velocities. So each ice class has a certain velocity. And now I start the simulation. We're traveling from this point to this point. You see that the situation is changing, the ice is moving. And while the ice is moving, the algorithm calculates the best route through that ice field. For that calculation, we needed 20 minutes, and it covered a distance of about 70 kilometers, I think. Is that fast enough, 20 minutes? Is 20 minutes something you would wait for a route? Maybe? Please tell us. So I will conclude now with an outlook. So what is most important things to do so that we can have route optimization ready and usable for you? The ice classification needs to be improved. So it's very often wrong what these ice classes do. And we also have to have more imagery. So one image per day is not enough. We need more images every hour or so. We hope that maybe even open publicly available satellite images can be used for this. We also need more data about performance of ships. So we could hire a lot of people, students for example. It's a good student job to just analyze a lot of icebreaker tracks on satellite images. So we have these characteristical ship curves. And of course we need to test it over and over again and throw the result to the user, get feedback. So it's kind of design-driven development. One platform where this could be visualized, I have a suggestion. It's called ICC. That's a platform we are producing at the moment. It will be available from November onwards. First only for Svalbard, but in the beginning it's definitely free to use for you. This is already a kind of a Google Maps for the Arctic. You can zoom in, you can update CS concentration, you can get low resolution Sentinel-1 images via a low bandwidth internet connection. You can display the animation, and even forecasts can be displayed in there. So now I would like to thank also my partners in the MAP-BORealis project. These are the heads behind the project. It's Dimitri Murashkin and Christine Eis from the University Bremen. They did most of the research work here. And it's me and my colleague Panagiotis Kontouris who are doing most of the software engineering and the user feedback and surveying. And as a last slide, I have a call to action for you. We are looking for a follow-up project. And for this, we need partners. So if you fulfill one of these points here, you have icebreaker data, for example, you have algorithms, or you have Earth imagery we can use, please contact us if you found this interesting, what I just told you. And as a very last call to action, Again, we have this icesurvey.org. If you haven't done the ice survey and you are an ice pilot or a master mariner who deals with shipping in ice, please do the survey. Now I will be available for the question and answer session for you, and also please visit our virtual booth in the virtual exhibition area here. Thanks.